So welcome to the second video of particle sizes, and today I would like to talk about particle size distributions, while in the previous video I talked about individual particle sizes. And for today we have the following schedule, or for this video, not today. So the question is, where do we need particle size distributions? In the last video I already gave some examples about the importance of particle sizes, and I again want to start with some new examples. And then I want to show why size distributions are important in comparison to the size of single particles, as we learned in the last video. And then, when we hopefully learned this, I would like to introduce the theory behind particle size distribution. And then I want to guide you through a digital analysis, why I will not introduce the software today, but how to do it and how you would do it with the software. So this is basically the schedule for this video, and I would like to start with a very, at least I really like this example, and this is about cacao or chocolate. So what you see here is an overview about cacao production from this year, and cacao is basically grown by farmers as these fruits here and plants, and then they are farming and processing them that we can make, for example, chocolate out of it. And what you see here are the main producing countries, and it's quite obvious that Ghana and Ivory Coast, especially Ivory Coast, are the most important producers, right? And a lot of cacao comes from this region in Africa. Then we also have some parts in South America, and also here Indonesia is an important player. And what's really interesting when you know who are the main producers is if you check this table, and here you see the consumption, mainly in terms of chocolate, of course, and you see that Africa is the main production country, but consumption nearly does not exist, while Europe, US and Canada, we are consuming a lot, but we don't have any production. So here's a strong export, right, which could be a very nice market. But if you take a look about the profit share, and this is the interesting part for chocolate, you see that only a little bit goes to the farmer and local areas, while most of the profit share here, production, marketing, grinder, processing, and retail and supermarket merchant, stay in Europe and the US. So it's a very unequal and unfair market when you look at this, because the cacao is produced or is grown, is farmed, the fruit in Africa mainly, while the chocolate is made mainly in Europe and the US. And this is where we earn the money and where the money stays. So what does it have to do with particle size distribution? Maybe a good question. And then let's take a look a little bit at the chocolate production process. And what you see here is chocolate going into these 5 press roller, it's called. It goes in, something happened, and it goes out. And what you have here is the already some part processed fruit or plant, and then you mix, you have small small cacao particles which are crushed already, right? So you take the fruit, you take the parts you don't want away, then you dry everything, you crush it, and then you mix it with cacao butter, and then it goes into these 5 roller press. And this is what you see here. Sorry, I showed it the wrong way. So it starts here and goes through this, and in these 5 roll press, the particle size of the cacao particles here from the fruit is further decreased. And what you want is a particle size below 30 microns. Why 30 microns? Because 30 microns and below, our tongue cannot taste the shape anymore. So we want to have a chocolate where you don't feel like the texture of the particles. So they have to be very fine. And this is what you have here in these 5 roll press. Then we have this called high shear device, and this is an add-on of this patent. And then an important step is called conching, and in conching you again press and mix the chocolate with the cacao butter also, so the fatty part. And you do this for 12 to 24 hours and do this under a certain temperature, and then you have your final chocolate. So what you have to do is you have to set the correct particle size for your cacao powder, which is in here, to have the perfect properties the consumer wants to have. And the idea of this patent is to add a high shear device. Why? And this is what you see here, is you have particle size, and this is what you want to get out of your process, right? And the new invention tells you that they say, I mean, it's years ago, but it's a nice example. So this is what you want to produce, 25 microns. And this is the flow rate you can do after the old process. And now you can have a much higher flow rate, but still have 25 microns. So the aim here is to reach a certain particle size. This is what you sell. This is your product property. So chocolate quality depends strongly on the property of the particle size of the cacao powder. And what you can do as a small example, if you want to try out, I really like to do this in the lecture, you take dark chocolate and you take milk chocolate, right? And then you eat them. I will not do this now because then I have my mouth full with chocolate. And then you try to figure out what is the difference between the dark chocolate and the milk chocolate. And don't tell me it's the taste. I know they taste different because one has milk and the other one has chocolate. But there are differences in the experience in the mouth. Try to figure out. I give you one example. The dark chocolate is said to be more sticky. But there are also some other things. So try it out, send it into the comments if you find the difference, how dark chocolate feels in the mouth, how milk chocolate feels in the mouth. And the question is, why dark chocolate has this more sticky feeling? And this is what you see here. So here we see size distributions. And these size distributions are two diagrams. Both are the same data, same measurements, but different depictions. And you see milk chocolate is the black one here and here. And then we see chocolate with 70% and with 99% cacao. And you see that the particle size of the cacao decreases for chocolate with more cacao in it. And this is not because the milk powder is larger, it's because that all of them are below roughly 30 microns, right? Here's 30 microns and all of them are below this. This is what we don't want to have. But for the dark chocolate, the cacao powder is grinded longer. So you have smaller cacao particles in your chocolate, and this gives a different experience in the mouth. So this means the product property of the chocolate is determined by the size of the powder, of the cacao particles. And this is represented as size distribution here. And here you see this peak is the main amount of particles, and this is in milk chocolate around 20-30 microns, and here when we talk about 99 it's around 8-9 microns. So it's a huge difference. And now you could argue and could say, is this really a difference? If I look at these red and these blue curve, they are very close together. Very good question. This is why we repeat measurements. And here you see for the black curve a repetition of 5 measurements. These are 5 curves and they nearly look aligned, right? So we really can say these are significant differences, what we see here. So this means we have an example, cacao, and the size of the cacao powder determines the properties of the chocolate. And I would like to explain you these two diagrams. What you see here is called cumulative size distribution, large Q. X is the size here, X, right? Particle size in X. And dq or small q is probability density function. And the cumulative size distribution is the easier one, to my opinion. So we have the particle size in length on the x-axis. We have the quantity fraction as part of the total quantity. So what do? We take the quantity fraction, from x min to xi, and we divide it by the total quantity of all powders or of all particles. So this means we measure from a starting size 0 to 1 micron. And all particles in this block is divided by the total amount of particles. So we get a percentage of which fraction is in this area. And then we go from 0 to 2 micron. And we measure all particles and then we divide by the total amount, and so on and so on. And this is what you see here. It goes from 0 to 100, 100%, or 1. From 0 to 1 would be the same depiction, and this is in the size range from 0.1 till 200, but the measurement is not done from 0.1 till 200. It starts here at 0.3 and ends here at 80 or something. Okay, and in this interval we measure all particles and put them in their size fractions, and this is what you see here. This function has certain properties, and one is that if x is smaller than the minimum, so if the particle size I'm looking at, so I start my measurements, let's say at 1 micron, and I look at 0.1 micron, for sure there will be no particles, right? Because I'm below my measurement value. And if I'm above my measurement value, so I measure till 100 micron and I take a look at 150 micron, my result will, or my diagram will be 1 or 100%, right? Because it cannot increase more than 100% because I'm out of my measurement box. And the third property is that x min, or if x is somewhere between x min and x max, the function is continuously rising, right? Because if you take a look here, the function has to rise because we add more and more particles. What could happen that in one fraction we don't have new particles, so then it would just go straight like this till we count more. We don't lose particles, right? Because we are cumulatively counting them from the lowest value to the highest value and then divided by the total amount of them. So one part you see here is xi. I is where I'm in my x-axis, right? And this QR is called quantity type. And quantity type means there are different ways how we can measure the size. And you already saw this in the last video, these equivalent diameters, right? Optical or by settling and so on. And this is what you see in these tables. So the indice here, 0, 1, 2, 3 or 3 star, the 3 star is not always given, tells you how I measured my particle size. So 0 would be number, so it means I count them, and this is very common. 1 would mean I measure their length. I don't count their length. I don't count by length, I measure length, and this is not really happen. Area, volume and mass. And mass is again very common, and if we take a look, so mass is very often also as 3, so they are vice versa used. And if we take a look here, Q3, D3, so this is measured by mass or by volume. So you just have to multiply or divide by density, that's the same. So this is the information of this QR here. So the next one is the second diagram we saw below. Oh, sorry, yeah, here, this is, I didn't have to jump. Now I would like to give you an example. And the example is that we make this diagram. So what you see here is a working example for sand. So I sieved, and this is the sieved, we are using a sample out of sand. And there is sand. Why sand? Sand is because, as you saw in the last video, I have some concrete here, right? And we need, to make concrete, we need sand. And the sand has to be very specific properties, and these properties are given by the size. So the sample you see here is standardized sand, which is used for certain investigations, and then it's sieved. And here you see the number of the sieve, number 1, number 2, number 3, number 4, number 5, number 6, number 7. Number 8 is a fictive one, which I need for the calculation. And here you see the mesh size. So the mesh size is the size of these meshes. So this is a large mesh size, middle mesh size, small mesh size, right? The large particles cannot go through, the middle one cannot go through, only the small one will stay here, and the smallest one will go to the ground. So, and then we see it's weighted, so it's a mass, so 3 star, And this means in the lowest sieve we have 3.12 gram. And in the next one it's 0.063 millimeters, so 63 micrometer. We have 72.5 grams in the sieve, and so on and so on. So this is what I get out of my sieving experiment to measure my sand. And with this I can now work. Basically I would do it with a computer, right? So make an Excel, or I would really recommend a Python code. So the first thing is you just sum up, and this is the sum in gram of your total mass. So this is the total mass which was sieved. And then we can calculate the mass fraction, right? So the mass fraction is basically a percentage, and this is, if you divide mi from the sieve to the total amount, then you will have here 0.002. This is about 5%, 26%, 28%, and so on. The next one we could calculate is the called throughput. And the throughput is nothing else which goes through, but which also gives you the cumulative size, because the throughput basically adds or sums up these single numbers. This is what is in sieve number 1, what is in sieve number 2, what is in sieve number 3, and now you count from the left, from the smallest, this plus this is this, plus this is this, plus this is this, right? The remaining is just, I put it in gray, it's not so important, just to have it, it's 1 minus. And if you now make a diagram out of it, you get this cumulative size distribution of the example I gave you. And again, we have this curve with increasing between 0 and 1, or in percentage 0 and 100%. And this is just a depiction of these DIN norm or standardized sand. So this is cumulative size distribution. The next one is the called probability density function. And here we again have the particle size on the x-axis, but we have now the quantity fraction as part of the total quantity in a specific interval related to the size of the interval. What does it mean? It means that the equation basically is the same here, but we add the size of the interval. So it means we not only divide the quantity fraction by the total quantity, but we relate it to the size of the interval. So basically we look in each sieve, and then we take the statement, okay, in this sieve this amount, in this sieve this amount. And the distribution is a little bit different. It means that each value smaller or larger than x is 0. This is what we saw also in the first diagram I showed you, right? And we have a maximum at the inflection point of q, x, y. We will see in a minute why that. And if we would do this for our data, right, for the sample data, we would not get the cumulative, but now we would get the probability density function. And this looks a little bit different. Here is the size, and here we see now very clearly the maximum, and this is the largest fraction in my sample, right? So most of the particles are in this size here, and then it's decreasing. So now you could also work with some statistical numbers, but I will make an additional video for this. Here I just want to introduce the diagrams, and this is the probability density function. So there is a relation between probability density function and cumulative distribution function, and this is, if we take a look, the definition of the probability density function, quantity fraction divided by total quantity times size of the interval, and size of the interval is delta x, right? X is the size, and this means quantity fraction, total quantity, relates q to the size of the interval. So the small q is the large q divided by delta x, and this is what you see here. So basically this is the derivative of this, or the other way around. The large q is the integral of the probability density function. This means the area under the probability density function must be 1 if you go from 0 to 1, or 100 if you put it in percentage. So the last one is the histogram. The histogram depiction is basically the same. So the plot can also be depicted as a non-continuous representation. This means you have single bars, right? And then the equation stays the same, but you just call them differently. And what is important at the end is if you would plot them not as a graph, but as a histogram, this is the same data. You get these really nice representation of the particle sizes and can make a nice histogram out of it. So finally, I would like to show you if you compare different samples, and here I took play sand. Play sand is normally smaller. It's the one you can put in the playground, or which you can put if you need sand between briquettes, for example. And there you see a clear difference based on their sizes. So in the cumulative size distribution, this is the data I showed you before. And this is another one, the play sand. And here we very clearly can compare them and see, okay, the play sand is much smaller because it has much larger amount of particles in this size fraction, while the norm sand has a larger fraction here. Good. With this we are nearly done, but I want to have a task for you to train your knowledge, and this is what you see here. So it's a small diagram. You just can copy it, or you can put the number into an Excel sheet. Here's the number of sieves, mesh size, it's the same, it's normed. You need these ones, so it's doubling, right, from here to here to here to here. It's doubling, and you need this as an upper end. So this is empty, and I made a small mistake. The mistake is this should be an empty row, so this is not the sum. Calculate the sum, that's the first you have to do. And then try to use the video and fill up these gaps here and make the diagrams as I showed you. Then you have a very good understanding of particle size distributions, how to deal with the data. And finally, I hope that you understood why particle size distributions are important, that you see the difference to single sizes. We learned in the previous video that you have an understanding of size distributions in terms of what is a cumulative size distribution, what is a probability density function, what is the relation between both, how can we plot both, right? So how would we do the digital analysis? Thanks for watching the video, and if you have questions, please let me know.